Hey everyone, and welcome to Chapter 10 on exponential and logarithmic functions. We're actually starting at the second section on evaluating and graphing exponential functions, and so we're going to get familiar with those a little bit. Now, a lot of the functions that we've talked about have applications in various settings, but a particularly important application is when you look at population growth, or in particular, growth of a disease. So let's suppose, totally hypothetical situation, we have a person and they get infected by a virus that is in no way, shape, or form all right, it's the reason that we're all stuck in this situation. So okay, so we have a person and they contract a virus, and before they start exhibiting symptoms, or maybe they don't exhibit symptoms at all, they come in contact with two other people. Well, if the proper measures kind of aren't being taken, right, they're not wearing masks or socially distancing, then those two people can contract the virus. They just come in contact with two other people, then they can get infected. And if those people come in contact with another two people, then they can get infected. And the process repeats, but since everyone is infecting two other people, the number doubles every time. So, understanding exponential functions will perhaps put some perspective on the current events of the world and what makes the spread of disease so scary, especially if it's really contagious. All right, an exponential function where a is greater than 0 and a is not equal to 1 is a function of the form f of x equals a to the x. So here's some examples. We have 2 to the x, 3 to the x, 8 to the x, 1/2 to the x. We would know how to evaluate these by plugging in, let's say, 2. Then I would have 2 squared, 3 squared, 8 squared, and 1/2 squared, and -3 squared. We're going to keep our eye on this -3 to the x because it's not, you'll see in a minute why it's not sensible to define an exponential function like this. So these first four guys are always real numbers regardless of what the value of x is, right? Could be positive, could be negative, could be rational even, could be 1/3 or 2/5 or 7/4 or whatever. But this guy, this -3 to the x, is not a real number if x is a fraction with an even denominator and odd numerator, I guess. So it's not necessarily the case if you have the quantity -3 raised to the x power, you get something that's a real number. And so we don't, that makes it really, really hard to graph because there's lots of rational numbers that fit this description. So we just kind of do away with this business and stipulate that the number that we're raising to the x power has to be positive. All right, so let's graph some examples. So let's start with -2. If I plug -2 in to f of x, I get 2 to the -2, or 1/2 squared, or 1/4. Remember, negative exponents give us a reciprocal. 2 to the -1 is equal to 1/2. At 0, we have 2 to the 0, which is equal to 1. At 1, we have 2 to the 1, which is equal to 2. And at 2, we have 2 squared, which is equal to 4. So let's graph those points. -2, -1's at 1/2, 0's at 1, 1, 2, and then 2, 4. Yeah, we can do another one if we want. 3, 2 cubed is 8. So at 3, we're at 8 now. So let's see what this looks like. So we have a graph that's shooting off to the right, and then kind of melting into the x-axis, so to speak, on the left. If I can draw it nicely. And so let's look at the other one. Let's look at x and g of x. So if we plug -3 into g of x, we get 1/2 to the -3rd. Negative exponents are reciprocal, so actually this is 2 to the 3rd, or 8. You might be able to see a pattern here. So we end up with graphs that are mirror images of one another. So let's look at some of the properties of the exponential functions. Basically, we're going to get a different picture based on whether or not a is greater than 1 or a is less than 1. Remember that a is supposed to be positive. If a is equal to 1, you just get 1 all the time, so it's not interesting. That's why we're assuming a is not negative and it's not equal to 1. It's okay. Let's see here. For the domain, which is the x values I'm allowed to plug into an exponential function, there's no limitations on what I'm allowed to evaluate an exponential at. I can plug in any real number that I choose, and I get a real number out, provided that a is greater than 0 and not equal to 1. Now for the range, you kind of saw it on the other graphs that we just did, but these functions don't cross the x-axis, right? They melt towards the x-axis, but they never get past it. So actually, they never reach a y value of 0, and they don't reach a value that is negative either. So its range is really just 0 to infinity. So these graphs do not have x-intercepts. The y-intercept of the graph, though, is the point 0, 1. Right? When you raise something to the 0 power, you just get 1 back, so it's not super surprising. Some sample points. And then we have that the x-axis is a horizontal asymptote for the exponential function. We're going to talk about what that means in just a second. But the only real difference, even though the two pictures look significantly different from one another, the only real difference is the direction in which they are going. So if a is smaller than 1, it's decreasing, going down and to the right. But if a is greater than 1, then it's going up and to the right. So this thing that I mentioned in the other slide, asymptote, it is just a line that is distinct from the function you have. and the graphs of the line and your function become arbitrarily close together. What that means is they get closer and closer and closer and closer to one another. And so in the case of exponential functions, the x-axis satisfies that. You can see that these two functions go towards the x-axis, but they're never going to reach it. Some other examples of asymptotes would be if you had a function that looked like this, that approached both the y and the x-axis. This is the function 1 over x. Then it's possible to have multiple asymptotes. In fact, not only is it possible to have multiple asymptotes, but it's also possible to have infinitely many asymptotes. So you could have a function that looks like this, or just kind of repeats over and over again. So an asymptote is really just a line that your function gets close to. It might touch your line in a few places, but kind of in the long term, it's only going towards the line and not equaling it. All right, so we can transform exponential functions in the same way that we can transform quadratic ones. This is very similar to what we went over in section 9.7, talking about the transformations. They work pretty much the same way. So here we have f of x in green there, 3 to the x, the normal version. And then we have g of x, which is 3 to the x minus 2. And so you're doing the x minus 2 before you evaluate the exponential. And just like in the case with quadratics, that means that we are shifting to the right 2 units. And for h of x, we're subtracting the 2 after evaluating the exponential. And the net effect there is that we move our graph down by 2 units. And so you see that when you move a function with an asymptote, like f of x or g of x or h of x, you move the asymptote along with it. You move everything about the graph down 2 units. All right, so let's see if we can't use our sleuthing abilities to identify which graph is which. So let's see here. Letter A is 2 to the x. Now, I know that 2 to the x at 0 is supposed to equal 1. So the only graphs that equal 1 at 0 would be this guy and this one. So that narrows it down to 2, and then you gotta ask yourself which of the 2 is it? Well, at the value x equals 1, 2 to the x is supposed to be 2. And you see that that's only satisfied by this one. So this is the graph of A. The value of x at 1 in this first picture is 3. So actually, we can kind of already determine that this is going to be the graph of f, and kind of narrow things down for ourselves. All right, 2 to the x plus 1. Well, it's going to be the graph of 2 to the x, but shifted to the left by 1 unit. So this is a graph that needs to equal, it needs to have a y value of 1 at -1 instead of 0. And it seems like there is only one graph that fits this description. So this has to be B. 2 to the x minus 1 is the graph moved to the right by 1, so that at x equals 1, the value should be equal to 1. And there's only one picture that fits that description. That would be this one. All right, and then we have these last two, 2 to the x plus 2 and 2 to the x minus 2. Well, these are vertical shifts. So the plus 2 represents a shift upwards. That would make this picture D, and this last guy that's left would have to be e. So when you first look at this picture, it's kind of overwhelming, but you want to make sure that you're looking at the important features, like what points is this graph actually crossing, to help you kind of narrow down what you have. All right, so we've really just worked with integers for the base of the exponential, but there is no rule that says that it has to be an integer or even a rational number. So we have this really important base for exponential functions. It comes out of a sequence of numbers that looks like this. Right, so this first term is 1 plus 1 over 1 to the 1 power. That's 2. This is 1 plus 1/2 squared, 1 plus 1/3 quantity cubed, 1 plus 1/4 quantity raised to the 4 power, and so on. The terms in that sequence approach a particular value, what we call e. It's roughly 2.718281827, and we call this number Euler's number, or the natural base. So that's an important base for exponential functions. All right, for the very last thing, we have this property of exponential functions that they are 1 to 1. And that means that if you have a to the x equals a to the y, then the two exponents have to be the same. You don't have this situation that we ran into with quadratics where two different inputs can give you the same output. Every output is going to be distinct in an exponential function. So let's put that into practice. We can use that to solve some kind of basic exponential equations. So this first one, 4 to the x equals 256. Well, let me think about what my powers of 4 are. So 4 to the 1, 4 squared, which is 16. 4 cubed, which is 16 times 4, or 64. We have 4 to the 4th is 256. So this is 4 to the x equals 4 to the 4th. Or, in other words, x is equal to 4. So that's not too bad. And you can kind of apply the same strategies that we've been using all over the place for solving equations. So this middle one, you can add 23 to both sides. You'll get 3 times 10 to the y. Actually, this is supposed to be 33. So we add 33 to both sides. We get 300. Divide by 3. We get 10 to the y is equal to 100, and we know that 100 is equal to 10 squared. So y is equal to 2. All right, for this last equation, we have 2 to the 3n minus 1 equals 1 over 64. So let's think about our powers of 2. We want to write this 1 over 64 as some kind of power of 2. So we have 2 to the first power, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th, 64. So I get 1 over 2 to the 6 is equal to 2 to the 3n minus 1. And I know when I have an exponent in the denominator, I can take the reciprocal and make the exponent negative. And now we can use the one-to-oneness property. And we get that n is equal to negative 5/3. Alright, so yeah, that's about it for exponential functions. What we're going to do next is take a look at logarithmic functions, which are, in some sense, the opposite of exponential functions.